Now, Faraday's law of induction may appear just to be an alternative form of EVBL for the EMF in a moving conductor. It turns out, though, that it has much broader significance than we might expect from our derivation. It is applicable to any circuit through which there is a varying flux, even when no part of the circuit is moving, and thus no EMF appears that we can attribute directly to a V cross B force. Suppose, for example, that the two loops of wire, as located in this diagram here, a current in circuit 1 sets up a magnetic field whose magnitude at every point is proportional to this current. Part of this flux passes through circuit 2, and if the current in circuit 1 increases or decreases, the flux through circuit 2 will also vary. Circuit 2 is not moving in a magnetic field, so no motional EMF is induced in it. However, a change does occur in the flux through the circuit, and it is found experimentally that an EMF appears in circuit 2 given by epsilon minus dT by dt. So we can see that now this minus sign makes more sense now, because if the flux is going in this direction, we can work out the EMF. In such a situation, no one portion of circuit 2 can be considered the source of EMF. The entire circuit constitutes the source. Here is another example. Suppose we set up a magnetic field with the toroidal winding of this figure here. So we link the toroid with a conducting ring and vary the current in the winding of the toroid. We have shown that the flux lines set up by a steady current in a toroidal winding are confined to the space enclosed within the winding. So you can see that these magnetic flux lines are confined within this space of the toroid, and the toroid is these loops of wire all the way around. There's a current being pushed through them. You can see the current being pushed through them here, causing, remember the cross product there, is causing the flux to go round in this direction. Not only is the ring not moving in a magnetic field, but if the current was steady, the ring would not even be in a magnetic field. Field lines do pass through the air bounded by the ring, however, and the flux changes as the current in the windings changes. So equation 1, this equation here, predicts an induced EMF in the ring, and we find by experiment that the EMF actually exists. In case you have not recognized it, the apparatus in this diagram here is a transformer with a one-turn secondary. The phenomenon we are discussing is the basis of operation of every transformer. To summarize, the flux may change in various ways. For example, 1, a conductor moving through a magnetic field. 2, the magnetic field may change. For case 1, where the conductor is moving with a magnetic field, we can use EVBL or we can use either of these. But for case 2, in these conditions, we can't use EVBL because there's no conductor associated moving through this coil or anything. So we can only use this equation here. So you can see, because of this, we're able to find out the EMF in this loop because we can use this. Finally, if we have a coil of n turns and flux varies at the same rate through each turn, the induced EMFs in the turns are in series and must be added, so the total EMF is... So we've got several of these loops. We can find the total EMF produced in these loops by using the number of turns d theta by dt. So knowing this flux going through, we just multiply up by the number of loops. So that's, you can see how that's becoming to look like a transformer. Let's do some examples, make this a little bit clearer. I'm going to do this example here of a certain coil of wire consists of 500 circular loops of radius 4 centimeters. It is placed between the poles of a large electromagnet where the magnetic field is uniform, perpendicular to the plane of the coil and increasing at a rate of 0.2 Teslas per second. What is the magnitude of the resulting induced EMF? So here's our wire, and you can see parallel to the axis we've got this magnetic field which is changing at a rate of 0.2 Teslas per second. So I've written down the rate here, dB by dt equals 0.2 Teslas per second. So solution, the flux here at any time is given by the flux equals the magnetic field density, which is flux per unit area, times the area. The rate of change of flux is d phi by dt equals the rate of change of that. The area is constant. Obviously, we're dividing through by dt here. We've already said that the rate is increasing at 0.2 Teslas per second. So we've got this bit here, so we can just plug that in. And A is simply pi r squared, so we've got that value. So we can just plug them in. 0.2, which is that, times this, gives us this number here, 0.001 Teslas meters squared per second. So the magnitude of the induced EMF is simply the number of turns now. So we've got 500 turns. We've calculated the rate of flux change, and so it's 500 times that rate, and that finally gives us in voltage. The EMF in voltage then is 0.505 volts. So we've induced an EMF of 0.5 volts through this coil.